Today, how everyone reads data, tables, figures, chart. We are trying to read data in a more visual way. Not only like a linear function, but data could also have other shapes. Hi everyone, welcome to our channel. My name is Canon.
My name is Laila, and today we're going to talk about our project for mathematical modeling, about using topological data analysis to understand topological features for crystal structure classification.
Many of you probably have heard about topology, at least like topologists can tell the difference between a coffee cup and a donut. This is because in topology, unlike geometry, it's only concerned with the invariant overall properties of a graph or set under successive deformation without regard to a specific size.
Humans are actually pretty good at looking at the wholes of objects, connecting structures. Often wholes are more intuitive than a long list of numbers. Because of this, a statistical method developed from topology began to develop, which is topological data analysis.
You may have ever seen movies where detectives like to stick the clues and the pictures on the wall and connect them with the red lines. And what topological data analysis does is actually the similar things. We collapse the data into points and represent the connection between them with lines. As more data is added, you can see the shape of the data and the connection between the data. The goal of the topological data analysis is to extract these shapes. In other words, the topological meaningful features of the data, so that reading the data becomes easier and faster. In this project, we will focus on understanding the basic concepts of the topological data analysis methods and learn how to use persistent homology and apply it to classify crystal structures. In addition to this, we will investigate what information about crystal structures can be provided by two types of diagrams, point cloud diagrams and persistent barcode, and how we can understand the topological features in them. So our first problem is how to construct a topological data analysis. There are two general tools to topological data analysis, which is mapper and persistent homology. Homology is the one that we will talk in our project. The mind map shows the main flow of a persistent homology. First, we have to input the data, give it a geometric realization, and turn it into something that we can discuss topologically, which is no longer a number. And it's mainly like a point cloud map or figure. We will talk about it later. Then the topological features are extracted by persistent homology, such as the number of holes and appearance and disappearance of holes. This is very abstract thing, so we have to understand the topological features, and they're different in different research background and purpose. Another path is to combine with machine learning, which is transform the data into machine understand data like vectors to explain the extent time of the holes and so on. And we will explain the details in a moment. Let's start with the point cloud plot. It begins to the initial preparation of topological data analysis. First, we input the data. In our topic, we are actually entering the coordinate position of the atoms in the crystal. Usually, the computer will help us to calculate their distance. At this point, if your data is a higher dimension and you want to simplify your data, you can project the data. Then, we construct the filter, which is a strange word. It's actually putting the circle outside of data points. You can see the circle. And then the radius of the circle will get bigger. The bigger the circle will interact with the neighbor circles and then create a connection, which is present as a line. And this is our first process for TDA. We can initially see the holes and the regions created by the data. Let's use this picture as an example. This is a huge hole with several points, and 3 of the circles overlap after deletions, which means that those 3 points start to have connections. And we can connect them with lines, create a 2-dimensional simply complex, which is a triangle. Zero dimension in TDA is a single point corresponding to bit number 0, and one dimension is a line formed by 2 points corresponding to bit number 1. Two dimension is a triangle formed by 3 points corresponding to bit numbers 2. And 3 dimension refers to a 3-dimensional triangle formed by 4 points corresponding to bit number 3.
Now that my partner Canon has explained the concepts behind the point cloud model, it's my turn to show you how it can be used for deeper topological data analysis. Persistent homology analysis is a topological analysis technique to study qualitative features of data that persist across multiple scales. It is robust to perturbations of input data, independent of dimensions and coordinates, and provides a compact representation of the qualitative features of the input. Persistent homology simulates the changes produced by the thickening of a point cloud at different scales of resolution, and then analyzes the evolution of the resulting shape across the different resolution scales. The qualitative features are given by topological invariance, and one can represent the variations of such invariance across the different resolution scales in a compact way to summarize the shape of the data. By using homology, a tool in algebraic topology, one can measure several features of the spaces, including the numbers of components. We can then represent the lifetime of such features using a finite collection of intervals, known as a barcode. Roughly, the left endpoint of an interval represents the birth of a feature, and its right endpoint represents the death of the same feature. In general, it is said that longer bars represent meaningful and relevant data, while shorter bars most of the time are considered noise. However, the interpretation of the lifetime of a feature depends entirely on the context. Now that we have a little bit of context, we can talk about how it works. The basic idea is to use the position of atoms in a crystalline structure as coordinates to generate a point cloud graph, which is going to be our input. Then we have to build a filtration, which is in few words is a nest formed by interconnected points. For this, we can use Vittorius-Rip's complex, an equation that connects points that are at a distance minor or equal to epsilon, a variable that we are going to define in a moment. This equation tells us if it exists a candidate for a simplicial complex. Inside a subset of points in our point cloud, the first term tells us that simplicial complex is part of a subset if all the points inside it are pairwise in a distance minor or equal to 2 epsilon. So to use Vittorius-Rip complex, we start with a distance epsilon equals 0, meaning that we have only individual points. Then we have to increase it. The factor by which this distance is increased has to be determined for each specific case. While we increase the distance, we are going to see the connections between different points, forming different shapes that we call simplicial complexes. Once the distance covers the entire dataset, we have a nested simplicial complex. The next step is to build homology groups. For this, we have to do a map that connects all our simplicial complexes as a chain. This will form different features such as holes, loops, or voids. This has to be done for each value of epsilon. We can then measure the persistence of each feature to get our barcode, which will describe if certain feature is significant for our data. The crystalline structure of a solid is the origin for many different properties, such as melting points, thermal conductivity, reactivity, color, shape, etc. Using topological analysis can allow us to see which characteristics in structures determine such properties, and therefore we will be able to predict properties in unknown materials.
Admittedly, topological data analysis as an abstract mathematical analysis requires a certain threshold of topology fundamentals to understand. However, we also believe that as a useful analysis tool, more people should understand this method, and we will try to expand all the basic topological languages or definitions to break up this boundary and try to let more people understand and use this tool.
I hope this information has gotten you a little bit interested in topological data analysis, and if you want to continue to learn more, stay tuned to our project. We wish you to see you in the next video.
Bye!